Ay, perdón, que me pillaron en el teléfono. No, pues nada, Antonio, que una casa muy chula, por cierto, ya está. Vale, pues no sé. A ver.
Empezaremos. Okay, we'll start now. Thank you for coming. Today we are going to hear a talk by Carolina. Carolina works in our group for about a year now, and she'll show a bit of results on the colloidalized systems that we've been working already for a long time. I think it's fine if you leave your webcams open, and also if you interrupt, also because it's better as a speaker, I think, if you can see reactions to people. Okay, so Carolina, please.
Okay, thank you, Antonio. I will share my screen. Okay. And sorry. Can you see my screen?
Yes.
¿Por qué salen los subtítulos aquí? Otra vez. Perdón. Okay, now. Okay, thank you for coming. My name is Carolina Rodriguez Gallo, and today I will talk about the work that I did during this last year. The name is Topological Boundary Constraints in Colloidal Spin Ice. And as this work is inscribed in the... Can you turn on your mic? Thank you. As the work is inscribed in the geometrical frustrated magnetism field, I will start explaining what is geometrical frustration. In our daily life, frustration arises when not all the desires can be simultaneously satisfied. In the same way, frustration in physical systems emerges from the impossibility of simultaneously minimizing all the interactions. In order to better explain that, I will take two Ising spins, and that means two spins that can only point up or down. When we have two spins, one near to the other, the minimum energy will be obtained when they have an antiparallel configuration, like here, for example. And if we try to arrange the spins along one line, we can put the first one pointing up, the second one pointing down, and then the third one pointing up, and so on. And we can arrange the infinite number of spins, and the energy will be always minimized. But how about if we bend the space and instead of having one line, we have a triangle? Now we can try to put our first spin pointing up, then we put our second spin pointing down, and the third one, if we try to put it pointing down, we will observe that one link will be not satisfied, whereas the other will be satisfied. And if we change the configuration of the spins the other way around, we put it pointing it up, we will also have the same result. So this system is geometrical frustrated. Why the community is looking for this kind of systems? The community is looking for these systems because you can generate disorder, glassiness, ground state degeneracy, and topological charges, and also emergent new phenomena, other emergent phenomena. Okay. The first pioneering work on geometrical frustrations date back to the 30s with Jack and Ashley calorimetric measurements of the entropy of water ice. In fact, they found that water ice had a residual entropy at low temperatures. But it was Pauling that solved this theoretical problem, and he claims that in an elemental tetrahedron, the oxygens have a crystalline structure. That means that they are ordered, whereas the hydrogens can have two stable positions. One like this one near the oxygen at the center, and one like this one far apart the oxygen of the center. He also claims that the minimum energy configuration was the one obtained with two hydrogens pointing into the tetrahedron and near the oxygen, and two hydrogens pointing out. As all of you can see, not only exists one only configuration with the minimum energy, so that means that the ground state is degenerate, and then we have a residual entropy. That's why we have a residual entropy. Later, in the 60s, Lip, Hu, and Rees began working on simplified two-dimensional models call it the vertex models. Here we have an image of one vertex model. And that was a nice system in order to understand what was happening in water ice, and also shows some other emergent phenomena. Then in the 90s, ice-like systems received renewed interest in the context of magnetism due to some rare earth titanates, like this one, also show a Pauling residual entropy. And the reason of that is because also follows the ice rule, the magnetic moments of the cations of this rare earth also follows the ice rule. So also have a ground state degeneration and a residual entropy. Okay, until now, all the measurements were indirect measurements, like the heat capacity, the magnetization, and so on. So a lot of phenomena, like for example, the Dirac strings cannot be observed directly. And because of that, the researchers want to work with two-dimensional systems where some phenomenology can be directly observed. The first realization of an experimental 2D system was done by Wong and some collaborators in 2006, and they lithographically fabricate single-domain ferromagnetic nanoislands. In fact, here we can see an AFM image where we can see how these islands are arranged in a square lattice, and they observe the magnetic moments of these islands by using an MFM. Here we see an MFM image. That was the first time that we had a real space imaging. Also was interesting because this work opens the door to design the collective behavior between the spins, because you can, here they decide to arrange the island in a square lattice, but you can also build some triangular lattice or other structures. And it was a nice system in order to mimic the behavior of rare earth and understand how this system works. In this context, our group builds the colloidal spin ice, that is a mixture of different techniques, in particular soft lithography, magnetic manipulation, and optical tweezers. And how the system works. The works is the system has these double well grooves that are grooves in the resist, and these grooves have this kind of profile, this bistable profile that have one stable minima here and the other stable minima here, separated by a central hill. And in each trap, we put a paramagnetic colloid that can be located in this minima or in this other minima. Each particle has associated an icing spin that points along the direction of the particle. In order to trigger the interactions among particles, we use magnetic fields that induce isotropic repulsive tunable interactions, and that's the system. Which are the advantages of this system in front of other? We have accessible length scales, and that means that that's because we are working with colloids, and we can observe them with a conventional optical microscope. Then we have also high time and space resolution, because we use a camera coupled to the microscope in order to follow the trajectories of the particles. Then we can also direct manipulate the spins, and that means the particle, because we use optical tweezers in order to order our particles in the crystal. And then that the interactions can be tuned without changing the sample, because we only increase the magnetic field, and we then increase also the interaction among particles. In these systems, for example, in order to change the interaction among islands, you need to put them near or far apart. So you need to change the sample. And how, another question that we can do is how frustration arises in this system. If we took, as an example, one single vertex with all the particles pointing in, and then we trigger the interactions, the repulsive interactions, all the particles will try to point out. So we will end up with this type of vertex. And if we only have one vertex, there's no problem, there's no frustration. But if we arrange the vertices in a square lattice, like in this way, we can observe how all the interactions cannot be minimized at the same time. So we will end up with a configuration that follows the ice rule, that that means having two particles pointing in and two particles pointing out. And our ground state now will be the type 3 vertex. In fact, in our group, we performed some experiments where by increasing the the magnetization and the magnetic field, and then the interaction among particles, we observe how the system evolved to a type 3, to have a more fraction of type 2 vertices. Okay, before going deeper in this system, I will explain what topological charges are. Topological charges follow this equation, where n is the number of pins pointing in, and zeta is the lattice coordination number. In the square lattice, zeta is 4, and for example, in a triangular lattice, zeta is 3. And if we take an example, this vertex, we have 0 particles pointing in, so 2 per 0, 0, minus 4, the charge will be minus 4. For even coordination lattices, the minimum value that can have this charge is 0, and are the configurations that follow the ice rule. For example, these ones that have 2 particles pointing in and 2 particles pointing out. And the minimum excitation that you can have are called monopoles with plus 2 and minus 2 charge. Whereas for our coordination lattices, the minimum charge that you obtain is plus and minus 1. But normally they appear in pairs, so the charge of the system is equal to 0. Why these charges are called topological? These charges are called topological because always appear in pairs. In fact, if we take a ground state with all the vertices in an ice group configuration, in a two-in, two-out configuration, in order to obtain one single monopole, one single excitation, we need to flip one spin. And once you obtain a plus 2 charge, you will also obtain a minus 2 charge. You can far apart these charges, and if the spins are magnetic moments, and the ices degenerate, this configuration takes the name of a direct string that can be seen as a floppy dipole, a flexible dipole. And in order to remove the charges, you need to bring the charges together, and then they will disappear, and also disappear in pairs. Exploiting the benefits of our system, our group studies the interaction among these 2 monopoles with this experiment, where they arrange the initial configuration like this, and that means all the vertices in a ground state, and then they created 2 charges, and they perform the following experiment. They apply a magnetic field, and they follow the distance between the charges in front of the time. And they observed that this behavior was in agreement with the theoretical predictions that predicts that there is a magnetic Coulomb law between these 2 charges. The colloidal spin ice is used as a model system in order to understand what happens in spin ice systems, and it can be used to build some NOR logic gates that are functionally complete ports capable of generating all the logical interactions that consist on this work is based on the motion of topological charges, and also is completely reachable. Or also can be a model system, the colloidal spin ice, to show how to store some binary information, as for example in this image, that our group demonstrate how to write UB with a colloidal spin ice. Until now, I talk about previous results, and now I will talk about the results that we performed during the last year. And in this work, we study the finite size effects of the colloidal spin ice by changing the boundaries of the system. We choose 3 different boundaries: the antiferromagnetic, the domain wall, and the open ones that mimics the experiments. And also we perform some periodic boundary, some simulations with periodic boundaries in order to understand what is happening. We also change the system size from L equal to 6 to L equal to 40, where L is the number of pins along this direction. Okay, this work started to be an experimental work, but due to COVID lockdown, we moved to Brownian dynamic simulations. And in order to do that, we solve the equations of motion given by the second equations of Newton. That is this one, where all the forces that are in this problem are the viscous force, the force that appears between the monopoles, the dipoles, when there is a magnetic field, the gravitational force of the trap, and a random term that stays for the temperature. As the particles are submerged in the low Reynolds number fluid, we can neglect the inertial terms, and then we end up having the overdamped equation of motion, this one, where these terms are the viscous forces proportional to the velocity. This other term is the force that appears, that generates the trap, this B-harmonic trap. And this other force is the force that appears between two colloids, two paramagnetic colloids, when there is a magnetic field. And this force is along the separation direction. In order to solve the equations, we discretize them and we apply a velocity parallel algorithm. Okay, first I will show the results with antiferromagnetic boundaries. We set the boundaries, we arrange the boundaries in this way. So we alternate one spin pointing in and one spin pointing out. And in the bulk, we started with a random configuration where these dots correspond with the charges that follows these colors. For example, the red one are a +4 charge, and the blue one, the -4 charge, and so on. And the arrows are type 4 vertices, and the gray areas are type 3 vertices. We observe how, for values of, in order to perform our experiments, we apply a magnetic field ramp from 0 to 25 milliteslas. We observe how around 8.3 milliteslas, all the highly charged defects disappear. So the defects with +4 and -4 charge disappear, and we only have monopoles or type 4 vertices. And we also see how a lot big areas starts to fall in the ground state. And we surprisingly observe how for 25 milliteslas we obtain a fully ground state. That was quite surprising because it seems that the phase space is decreased, and this was not observed previously, where we can see here in these experiments how the fraction of vertices never reaches 1, and also in some artificial spin ice experiments they observe these line defects, but they never observe a full ground state. Then I will talk about the results of the domain wall boundaries, where we intend for domain wall boundaries like that, and that means that in the left and in the right part the spins point in, and in the upper and the lower part the spins are pointing out.
I have a question.
Yeah.
Sorry. I wanted to ask you. So do you have the effect of temperature? Do you have it in your simulations?
Yeah, there is a random term, as I explained here.
Yeah. That
stays for the temperature. Okay.
So how are your magnetic energies compared to that temperature? So do you have an estimate of the magnetic energy of two particles next to one another at one of these values of the magnetic field?
Sorry, can you repeat the question?
So the magnetic energy between the two particles will depend on the distance and the value of the magnetic field, because I understand that your particles are paramagnetic, right?
Right. Yeah.
So do you have an estimate of what's in terms of KBT of?
No, I don't have this estimate. But you don't obtain jumps due to temperature, or almost, or you obtain it, but for small magnetic fields values. If I understand correctly your question. At high magnetic field values I think is negligible, the flips of the temperature, because you obtain a stable ground state. I answer your question?
Yes, thank you.
Okay. So for for magnetic fields around 8 milliteslas, we observe also that highly charged defects disappear, and at 25, and we also observe an accumulation of charges in the edges, and in particular, +2 accumulation of charges in the regions where the spins are forced to pointing in, and accumulation an accumulation of negative charges in the region where the spins are forced to pointing out. That was a result that we didn't expect, because we expect to find a curve like this This is our results with boundary conditions, with domain wall boundary conditions with a 6-vertex model. And instead of that, we are working, in fact, with a 16-vertex model. So that makes sense that we don't find the same results. We find that our Arctic region is only this square that is near the edges. After that, we perform some simulation with open boundaries. We also apply a magnetic file RAM, and we start from a random configuration. Open boundaries mean that we don't force the particles in the boundaries to be located in anywhere, and we let them free. And we also show an accumulation of charge in the boundaries. We observe how this accumulation was only made of negative charges. In fact, we see how this system is not non-topologically protected. In fact, we start with a sum of charge equal to 0, and we end up in a saturation point with a charge with a negative total charge. This negative charge is size dependent. In fact, these lines correspond to a system of 6 per 6 vertices, whereas this other line corresponds for a system of 40 per 40 vertices. We always find some defects, some line defects in the bulk, and we observe how the fraction of type 3 vertices decreases by decreasing the size of the system. And the reason of that is because the ratio between the volume and the perimeter is approaching 1. Then, as I said, we perform some periodic boundaries simulations in order to better understand the system. And we observe that even systems, that mean systems with L equal to an even number, here, for example, L is 2 per 2. In even systems, the defects line appear always in pairs. Whereas for odd systems, for example, this 3 per 3 system, the line, we always find one line defect. And that's why we find this zigzag behavior, because we have one even system and one odd system. And for even systems, we will have less amount of type 3 vertices because we will have two line of defects. Okay, here in this image, we compare 4 boundaries, the 4 boundaries for different system sizes, ranging from L equal to 6 to L equal to 40. We observe how the value of the file where we obtain a total ground state changes and depends on the size. In fact, here we observe how for a small system like 10 we obtain a fully ground state at 10 milliteslas, whereas for a 20 per 20 vertex system, we have this value at 20 milliteslas, and for a really big system, this ground state never appears. We also observe how periodic boundaries can reach a totally ground state for small systems, and that open boundaries and domain wall boundaries have a less amount of type 3 vertices in the final state. That is the results for, Okay, after that, we decide to play a bit with the antiferromagnetic boundaries and to introduce some domain wall defects in the corners, as I highlight here with the circles. By performing some simulations, we observe how there exists a kind of analogy with the Gauss law. In fact, if the input flux, the input numbers of spins pointing, like if we had an unbalanced number of particles pointing in the boundaries and pointing out, we find an enclosed topological charge. And this topological charge then can be fine-tuned by modifying the boundaries. That was really interesting, and we use this behavior in order to find novel phenomenology, like, for example, symmetry breaking mechanism and also confined topological protected strings. In fact, here I'm showing the results with the system that has 4 defects at the corners that the particles are forced to pointing out. We perform also magnetic file ramps, and we observe how around 8 milliteslas, these defects are connected with lines of defects, and from 7 milliteslas to 25 milliteslas, all the phenomenology tries to separate these lines and to put them near the edges. We perform several repetitions of the experiment, and we observe that there are two final states. The state 0, that is the state that connects the defects along horizontally, and the state 1 that connects the defects vertically. This we perform 100 times the same experiment, and we observe that this is a bistable system. In fact, we have the same probability of obtaining the state 0 and the state 1. And then we also decide to in order to better characterize that, to choose an ordered parameter that was the spin direction of the direction of the associated spins of the defects, and we obtain these two branches, where the upper branch stays for the state 0 and the lower branch for the state 1. Then we decide to perform some experiments in order to have a proof of concept of that. So we build our soft lithographies in the clean room. We prepare the colloidal suspension, that this time was generated with two kinds of particles. The big ones are the paramagnetic ones, and the small ones are silica particles that are heavier and non-magnetic. And we use these particles in order to fix the position, to induce local jamming and to fix the position of the paramagnetic particles. Then we also do a layer-by-layer charge deposition on the photolithography in order to avoid sticky problems. We put the sample under the microscope here. We wait until sedimentation. We then mount the sample with optical tweezers, as I'm showing here in the video. We randomize the positions, and then we turn on the magnetic file in order to see the interactions and what happens. Okay, we perform several experiments. Here I'm zooming the local jamming of the paramagnetic particle with these three silica ones. In fact, the position of these particles remains stable, whereas the bulk moves freely. And we obtain two different states as we observe in simulations. In fact, we obtain these defects connected horizontally, or also these defects connected vertically. So we also experimentally obtain state 0 and state 1. Then we perform also experiments by introducing some defects in opposite directions, like this. And we observe the same behavior. The defects were connected by a line of defects at around 7 milliteslas. And then the whole process stays for just shrinking the region where we can find the defects. And we can end up having this line of type 4 defects. We also observe it experimentally. But we observed that the most probable configuration was not the one with all the type 4 vertices, but instead of that, in fact, this configuration corresponds with this white line. Instead of that, we have a lot of, we normally end up with a final state where we find a couple of charges or more than one couple of charges. So we claim that we find a way to find topological strings and confine it in this region. So to conclude, we found that antiferromagnetic boundaries forces the system to a type 3 vertex ground state, and that open boundaries give rise to an excess of negative topological charge, and this behavior is size dependent. We also observe how to enclose topological, we also see how the enclosed topological charge can be tuned by changing the boundaries. And we observe emergent new phenomena as the symmetry breaking behavior and the confined topological strings. Thank you for listening. And if you have some questions, I will be happy to answer them. Thank you.
Thank you, Carolina. Are there any questions besides Carla's?
I have a question.
Okay.
I have more questions. So, so you started talking about the entropy of the residual entropy of ice. Mm-hmm. Introducing this concept of frustration. So, mm-hmm. In your system, can you measure the? So, do you have a way to measure the entropy and of your frustrated state? Have you?
We didn't do it, but the problem also with our system is that mm-hmm. there is a splitting on the energy on the 2-in 2-out configurations. In fact, we have different energies for this 2-in 2-out configuration and this other one, because as I explained here, The interaction depends on the distance between the particles, and as you can observe, this distance is higher than this one. So this vertex will have less energy than this one. So there is not fully degenerate our system. We have only two types of ground state. That means you can also have two types of, you have degenerate ground. You have two possible ground states. But for example, if you are forcing here the particles to be antiferromagnetic in this manner, you only have one ground state. So the system is not degenerate. In fact, we are...
Sorry. So you said you have so you have a degeneracy in your ground state because type 3 as a whole, right? So what you mean is that as a whole, you can have them as this or the opposite configuration. Is that
Yeah.
But then you're saying that type 4 has a different energy. Yeah, I see that. So it has a different energy than type 3. So it's not.
Yeah.
So it's not the same case as in water. That's the idea, right? Okay.
Yeah.
Okay. I see.
In fact, we are working on a system where we can find a fully degenerate colloidal spin ice.
Would there be any macroscopical quantity that would be affected by this residual entropy in case you had
some microscopical quantity?
Yeah. So in ice, right? You have is it like the heat capacity is so there's a sign in this heat capacity due to this, right? Due to this degeneracy.
Yeah.
So there would there be anything similar in your system? I mean, it's I don't know.
Yeah. I don't know. I don't think about it, but I think that I would need to think about it before I answer you.
Okay.
Pietro has something that I don't know if it's a question or a clarification. Pietro?
No te escuchamos.
No?
No, seguimos sin escucharte. Maybe you can write on the comments or... Just was a comment on the question of Carles.
No. Yeah, I think so. I think Peter is still typing, but maybe I can give a brief summary what I think of that he's saying. So the issue here is that particles are not exactly in the center of the traps. So there's like this continuous space. There's a continuous space of positions, no? But you can discretize this position, and then you can measure actually kind of this configurational entropy. Now, in these systems, it's true what Carolina says. You don't have a degeneracy at the ground state. No, you will have a zero entropy when you go to zero temperature. But in the systems that Carolina is working on, you might have something degenerate in the zero temperature. The question would be if you can measure the heat capacity in some macroscopic way, because I don't think that's necessarily trivial. It's okay. I'm guessing. I'm not sure if that's what you want to say.
Okay.
But there are other things that are not. I'm not sure if they could count as macroscopic, but you can see some signatures of this degeneracy on the case of the spatial correlation, because you start getting this Coulomb phase that has pinch points and things, and kind of characteristic shapes. Pinch points, it has an algebraic decay like this.
Okay.
I don't know if that's correct.
Thank you. I have another question if nobody else. So in your simulations, you have different boundary conditions. What about in experiment? Because so I understand that the experiment is also limited in size. So what kind of, or put it the other way, what kind of simulations give you the closer account of what you get in experiment?
What do you mean?
So sorry, yeah. So no, what I mean is that in experiment you also have some boundaries, right? So what are those boundaries? Or
okay, sorry, I understand. Normally we perform some experiments, like just filling the sample with some paramagnetic particles and leaving the particles on the boundaries free. So all the experiments until here, until this project, were performed with the boundaries leave it free. But we, in order to fix them, we use this strategy with this local jamming, and we build a bit-dispersed colloidal suspension, and we fix these particles to point there by filling one gravitational minima with these non-magnetic particles. But until here, all the experiments were performed with open boundary conditions. That means by leaving free the particles in the boundaries.
Okay. Okay. But then, so you showed a graph with the different defects that you get, or the different charges, right? The distribution of the charges that you get as you increase the fields.
Sorry, this one? No.
Yeah, but the experimental one, right? You have an experimental.
Okay. Yeah. These results were from these ones.
Yeah. So could you use, so I don't know, is there, can you look at this and then look at the results that you get from your simulations under different boundary conditions and see what is the most similar?
The most similar.
Yeah.
I mean, the experiments correspond with open boundary conditions. So I expect that the open boundary conditions mimic very well the experiments, but the simulations are performed with periodic boundary conditions, and this fits very well. But the point here is that the data, the experimental data, is not from the whole region, but they build a big colloidal ice, and they took the vertices. They only count the vertices in the inner region. In fact, here the system behaves like a periodic one, not near the edges, but in the bulk region, like in the center of the region, it behaves like a periodic system, and that's why I think that the data are like similar.
But I think also what Carlos is saying might be interesting, if we can kind of reverse engineer our fixed boundaries to have something that matches the experiment. I don't know if that's your point, but it's what I thought.
Yeah, it was along those lines. Yeah, sorry, I didn't.
But I don't know. I mean, yeah, in the end, it's just a matter of counting how many lines come in and how many lines go out, and that gives us an estimate of the charge, and I guess also about the path of the other. Yeah, but I think it can be done. Yeah. Okay. Is there any other questions? And if not, Carolina, thank you very much.
Thank you.
And thank you everyone else for coming. And today we have people who are normally not here, and that's very good. Well, now see you next year. We have a calendar already, but we have a lot of empty spaces. So if anyone wants to give a talk, it will be very welcome.
Thank you. See you soon. Bye-bye.
Okay. Thank you. Bye.
Have a holidays. Bye-bye.
Thank you.
Bye.
Thank you, Carolina. It was a very nice presentation.
Welcome. Thank you.
Bye bye.